onwards. But this morning I was discussing with someone, so he came to me to discuss something about the spectrum of an operator. So I thought I would give that example also today. Okay, it's a nice thing in the sense that he brings out the fact that the operator action may be the same, but based on the space on which you are looking, the spectrum will look different. Okay, a very simple operator. So what I will do is, first of all, so another example on the spectrum of an operator. So we will look at the nonlinear space X to be either, I will assume a bit of measure theory and analysis here, but many of you may be familiar, but at least intuitively you can understand. I will take this to be either L1R or L2R, the two different spaces. I will consider the same operator, same action, but on two different spaces. L1R by definition is the set of all functions mapping R to R. Let us even take complex valued functions such that integral mod f t dt, let me use the letter x, okay, x t dt is less than infinity, the integration is over R, minus infinity to plus infinity. Now, only technical point is this integral has to be interpreted as the Lebesgue integral, okay, not the usual Riemann integral. And another thing that you should notice is, remember, is that the 0 element of this vector space is not the function which is 0 everywhere, but the function which is 0 almost everywhere, except on an exceptional set whose measure is 0, it is 0. Okay, so let me make sure theta x. Okay, similarly L2R, which both these we use in signal processing, the stable signals and the finite energy signals. Okay, mod x t squared dt. These are the continuum versions of the little L1 and the little L2, where sequences we had, where the sum was finite, and those little L1 were functions defined on the discrete set 1, 2, 3, 4, etc. Now these are functions defined on the whole interval, on the continuum. So certain technicalities are required to define these integrals. And then the 0 element in both these spaces is the function f of, okay, theta x t is the function which is 0. I will write almost everywhere, that is except on a set of measure 0. In a sense, it can be 0 at some point, it can be non-zero at some points, but those points must not really count much. There should be not occupy too much space, okay, on the interval. That is what is meant by measure 0. We will see, roughly use these ideas. Okay, so the operator that I am going to look at is like f mapping x to x, and of course the norm in this space is norm x1 is that integral mod x t dt, and the norm in this space is the root mean squared, the mean squared x t squared dt square root, the standard norms, okay, the energy and the length. Okay. So now I am going to look at the operator, which is simply takes a function x and maps it to another function whose value at the point t is x t minus 1, like a delay. Say a delay has been introduced in the function. So the mapping is just the delay map. At time t, you get the information from of time t minus 1. So f is like a delay. Okay. So these are for top people talking delay differential equations and so on and so forth. Okay. So this is the operator I will take. Now first thing is, if x is in L1, the delay is also in L1. because when you integrate x t minus 1, you can change the variable, again it will become minus infinity to infinity x t, again here also. So, clearly mod f x of t integral minus infinity to infinity dt is the same as integral minus infinity to infinity mod x t minus 1 dt, which is the same as minus infinity to infinity mod x t dt. So, therefore, if this is finite, this will also be finite. So, therefore, the norm of f x 1 is the same as the norm of x 1. Therefore, as a mapping on L 1, when you take x is equal to L 1, it maintains the norms. Okay? It is a norm preserving operator. So, therefore, f maps L 1 R to L 1 R is bounded linear operator with norm of f equal to 1, because it is just unitary, it maintains the norm. So, therefore, it can be thought of as the linearity is very obvious, okay, from the definition that f of x plus y is the same as f of x plus f of y. This is very obvious. Both are delayed. Okay, delay preserves superpositions. Okay. Similarly, f maps similarly mod of f x of t square integral over R is by definition mod x t minus 1 squared dt. Again, by change of variables, this is the same as minus infinity to infinity mod x t squared dt, and therefore, if this is finite, that is also finite, it maps L 2 to L 2 and the norm is preserved. So, therefore, norm f x of 2 is the same as norm of x 2. Therefore, f is a bounded linear operator on L 2 R, and norm of f 2 is 1, norm of f is 1. So, in both these cases, whether I take x to be L 1 R or x as L 2 R, the shift operator is a norm preserving bounded linear operator. So, therefore, f maps x to x bounded linear operator with norm f equal to 1 for both one x equal to L 1 R and 2 x equal to L 2 R. Okay. Now, since it is a bounded linear operator, we are going to look at what is the spectrum of this operator. So, what is the spectrum? You see that many slight all kinds of nuances of analysis will come into the picture in finding this norm, in finding this spectrum. Simple important ideas of analysis. Okay. So, whenever you look at spectrum, first is point spectrum, then residual spectrum, then continuous spectrum, and the remaining is what is known as the resolvent set. So, let us begin with point spectrum. What is meant by point spectrum? It is all the eigenvalues. We are looking for eigenvalues. So, some number will be a point spectrum. In the point spectrum, if there is a corresponding eigenvector or eigenfunction, in this case corresponding to that. So, what we will show now is there is no point spectrum. There are no eigenvalues for this operator. Whether you are looking this as an operator, the shift operator as an operator on L 1 R, or you are going to look at it as a operator on L 2 R, it is not going to have any eigenvalues. So, let me make first claim 1. Point spectrum is empty. Okay. Reason. Suppose not. So, therefore, there must be an eigenvalue. So, some number, complex number will be an eigenvalue, which means some number lambda will be there, for which there will be a non-zero vector x such that f x equal to lambda x. So, this implies, therefore, this implies there exists a complex number lambda such that there exists an x not equal to the 0 element of the vector space such that f x equal to lambda x. This is what lambda in point spectrum means. It is an eigenvalue, and therefore, there must be an eigenvector. Eigenvectors are elements from that space, and they should be non-zero element space. Okay. Now, what does that say? That says all this f x equal to lambda x. F x by definition is x of t minus 1, and that must be equal to lambda x of t, right. X of t minus 1 must be equal to lambda x of t. So, now all these functions are in L1. For such functions, we have the Fourier transform defined. Okay. So, I can take Fourier transforms on both sides. When I take Fourier transforms on both sides, the question is, when I am dealing with L1, I must look at the L1 Fourier transform. When I am discussing with L2, I must take the L2 Fourier transform, the so called Fourier Plancherel transforms. So, I will simply take Fourier transform suitable, that is depending on which space you are working in. In L1R you take the L1R normal Fourier transform, and the L2R you have to take the Fourier Plancherel transform, so called, which is a little tricky, but then you finally get it. So, the same properties hold in both the cases. This will become e to the I omega x hat omega, because shift boils down to multiplication by the exponential in the case of Fourier transform. This will be lambda x hat omega, and that says e to the I omega minus lambda x hat omega is equal to 0 for all omega, because the Fourier trans in I should not put for all omega, for all omega in the case of L1R and almost every omega in the case of L2R, because in the L1R case the Fourier transform of an L1 function is continuous. So, if it is going to be 0 almost everywhere, it will be 0 everywhere, but in the case of L2R function, the Fourier transform is defined only up to a set of measure 0. These are all some technical points which we will gloss over. Okay. Now, what does that say? X hat omega, since x is the non-trivial vector, its Fourier transform cannot be the 0 function, 0 element of that space again, and therefore, what can I say? E to the I omega minus lambda must be equal to 0 on some positive measure set, but then e to the I omega can be equal to a number only at some discrete set of points which are of measure 0. Any countable set has measure 0. Okay. This implies x hat omega is equal to 0 almost everywhere, because e to the I omega minus lambda equal to 0 only on a set of 0 measure. Okay. And but then if the Fourier transform is 0, x must be the 0 function. The only function which has Fourier transform 0 is the 0 function, which is a contradiction. We started with, suppose there exists a non-zero function, then concluded that that function must be 0 function. and therefore contradiction because x is not equal to theta x we started with. So, basically therefore, this argument says the Fourier transform and these fellows are so well related to each other that if things are difficult here you look there, if things are difficult there you look here. In this case we had an equation where one side had the shifted one, the other side did not have any shift. So, then to convert all of them to a standard format, the shift is taken care of by Fourier transform, and then we get the result that x hat omega must be 0. So, there is no point spectrum, no eigenvalues for the shift operator. There are other ways of looking, but this is, see this is where, this one example where you see all the many notions of analysis coming into the picture. We got the Fourier transform, we got the Fourier transform on L1R, the Fourier transform on L2R, and being 0, why the way Fourier transforms get make the shift go into the exponential multiplication on the other side, all the aspects come into the picture. Okay. Therefore, what does that mean? We have absolutely no chance of any eigenvalue. Absolutely no chance of any eigenvalue. So, the next thing we have to look at is the residual spectrum, the continuous spectrum, and the resolvent set, which are all the points lambda which belong to each one of these classes. Now, we have observed, so that is the first point. So, claim 2. Every lambda, so that mod lambda is greater than 1, that is outside the unit circle, must belong to the resolvent set. What is the reason? We observed that if you have a bounded operator, you draw the circle of radius, the norm of the operator, the entire spectrum must be inside that circle, anything outside will be in the resolvent. In this case the norm is 1, the norm of the operator f was 1, and therefore everything outside the circle of radius 1 will be in the spectrum. Okay. Since norm of f is equal to 1, we have the set of all lambda such that mod lambda greater than norm f is contained in resolvent of f, hence therefore that is all, and but see norm of f being 1, that takes care of that. So, now we have this situation, let me erase this, no point spectrum, this is the disk of radius 1, everything outside is resolvent. Now, all we have to analyze is inside and on the disk. So, now the next claim is everything inside is also in the resolvent, the set of all lambda, so that mod lambda less than 1 also belongs to the resolvent. Okay. Now, let us see how we are going to do it. What is meant by it belongs to resolvent? F minus lambda I inverse must exist as a bounded operator, but lambda is certainly not an eigenvalue because nothing is an eigenvalue. So, therefore, f minus lambda I is already 1 1. Okay. All we have to show it is onto. The moment we say it is onto, open mapping theorem, bounded inverse theorem says f minus lambda I inverse is also bounded, and therefore, lambda belongs to resolvents. Okay. Since by claim 1 we have lambda does not belong to the point spectrum, and hence f minus lambda I is 1 1. Therefore, it is enough if we show that f minus lambda I is onto, then by bounded inverse theorem we have f minus lambda I inverse is bounded and therefore lambda belongs to resolvent of F. So, all we have to show is that f minus the f minus lambda I is bound is onto. The moment we say it is onto, one has been granted to you because nothing is in the point spectrum. You have onto bounded inverse theorem, you are done. Okay. So, therefore, I have to show it is onto. What do I mean by saying that I must show f minus lambda I is onto? That means everybody can be written as f minus lambda I of something. That is to show that for every g in X, we can find an X in X such that g is equal to f minus lambda I x. Therefore, g will be in the range of f minus lambda I, and this we can do for every g, and therefore, it is onto. That is all we have to show. Every g can be written as f minus lambda I of something. If I can show that, then f minus lambda I is onto, right. So, what we are going to do is, okay, let us solve. That means, I am given this equation, knowing g, try to find x. Given the g, solve that equation to find x. Let us see how we solve that. Okay. So, what does that equation say? This is a very nice trick that once my one of the professors taught me. I will tell you what it is. This is the same one. I had asked one question in the class, and his reply was fantastic. And the same question was asked by the gentleman who came this morning, and I gave back my professor's reply. Okay. So, this is a trick. I mean, this is a lesson I learned from him. This is a lesson which I keep telling with some of my math friends. Okay. What I do is, I look at this equation and I throw caution to wind. I will do all manipulations and to capture what x could be. In between, if you ask me, is it justified, is it not justified, I said, wait for a moment. I will worry about justification only if we get something meaningful at the end. If nothing meaningful comes after all the manipulation, why waste time even justifying it? So, and see the funny thing that happens. Okay. So, what does that mean? It is f of x minus lambda of x. So, g of t must be f of x. What does f do? It is a shift minus lambda x of t. G of t must be equal to x of t minus 1 minus lambda x of t. What is given to us? G of t, and we want to find the x of t. So, what we will do is, we will take this x of t minus 1 and push it to the remaining fellow to the other side, g of t plus lambda x of t. And now replace t minus 1. So, if I go to x of t, what should that be? This should be 1 more than this, and that will be 1 more than this. Okay. Instead of t minus 1, look at t. If it is t minus 1, that should be t. So, if this is t, that should be t plus 1. So, x of t is this. Now, this is the standard iteration process. What I do? I make a guess and then substitute that guess there, and then substitute that second guess there, and that is the standard iterative setup. Okay. Any iterative setup is of the form x is equal to g plus something acting on the x. So, you go on guessing an x and go on putting on the right hand side, you get the so called series. Okay. So, now what I do is, x of t is equal to g of t plus 1 plus lambda x t plus 1. This is g of t plus 1. If from here I will get x of t plus 1 is g of t plus 2 plus lambda times x of t plus 2. So, it is g plus t plus 2 plus lambda x of t plus 2. Then that is g of t plus 1 plus lambda g of t plus 2 plus lambda squared x of t plus 2, right. Now, what do I do? Again I calculate from here x of t plus 2 will be g of t plus 3 plus lambda of x of t plus 3. So, one more, whenever you have something here, one more on this side. So, I will continue this process, it will be g t plus 1 plus lambda g t plus 2 plus lambda squared g t plus 3 plus lambda squared x t plus 3. Now, how do we do the iteration? We go on doing it, go on continuing the process. So, at least heuristically what do you get? Continuing this process. So, I will keep only the claim 1, claim 2 now. So, continuing this process, you get x of t, I will put a question mark there, none of these things I have justified, g of t plus 1 plus lambda g of 2 plus t plus 2 lambda squared g of t plus 3, and it goes on like that, lambda cube g of t plus 4 and so on and so forth. Now, that is a mess. How do I know even the right hand side converges, and how do I know that even that is equal to x? It is only some guessing game that is going on. So, okay. So, suppose the series on the RHS converges. We will show that is an x which satisfies this equation. Okay. Then we see call the sum as x, then substitute there, you easily see that this equation is satisfied. Then what is f of x of t? It simply shifts. Okay. F is simply delay by 1. So, it will delay each one of these terms by 1. What will I get? In place of g t plus 1, I will get g t, and I will get lambda g t plus 1, lambda squared g t plus 2, etc. It will delay each one of these terms by 1 unit. Then what is lambda x? Lambda x of t is simply I have to multiply this. So, it is lambda g t plus 1 plus lambda squared g t plus 2 plus etc. If I subtract, what do I get? G of t. So, that implies f of x minus lambda x is equal to g, and therefore, we have x belonging to x such that f minus lambda I x equal to g, and we are done. Therefore, f minus lambda I on to what we wanted to show. Okay. So, the crux of the matter is I have to show that series converges. So, I now forget about how I got the series. I do not even care justifying the steps there. I made a guess. Now, I am going to show that guess works. I will show that series converges, and once it converges, I can do all this, and I verify that that is indeed the pre-image of any G. For any given G, we can find the pre-image X by this infinite series. This is a typical iterative solution in any functional equation, whether it is differential equation or integral equation or algebraic equation, whatever it is. This is the typical setup of the iterative, even matrix equation. This is how we set up the iterative procedure. Okay. And there we get the matrix eigenvalue to be less than 1, that is this mod lambda less than 1 sort of idea. Okay. So, now we have to prove the star. So, proof of star. We have to show that the series converges. Now, if the series, to show that the series converges, I have to show where should it converge? It should converge in that space. They are all, each one is a function in that space X. So, I want to show that the convergence in that space. Now, I say a series converges if this sequence of partial sums converge. Okay. But then since each one of these spaces is a whether I take L1 or L2 they are all Banach spaces. So, to show convergence is enough if I show that there is a Cauchy sequence. The moment I show Cauchy sequence, the fact that it is a Banach space will tell me definitely there is going to be a convergence. So, therefore, since X is a Banach space, it is enough to show that partial sums form a Cauchy sequence. So, let us go and see what is the partial sum. So, let us take the first n terms. It starts with gt plus 1 and therefore, it will end to gt plus n. Okay. So, gt plus 1 plus lambda gt plus 2 plus etcetera plus gt plus n, the coefficient will be lambda to the power of n minus 1. What will be Sm? It will start with gt plus 1. Let us assume that m is greater than n without loss of generality, and that will go on, and all these terms will be there, plus now we will have additional terms gt plus n plus 1, and it will go on up to lambda to the power of m minus m gt plus m, right. That will be what the mth partial sum is. So, what is the difference between the mth partial sum and the nth partial sum? You will see all these terms get knocked off and you will get terms only from here. So, I will write it as summation j equal to n to m minus 1 lambda to the power of j g t plus j plus 1, right. So, all the beginning terms get knocked off. Therefore, I want to show it is a Cauchy sequence, means I want to make the norm as small as possible. So, let us calculate the norm Sm minus Sm. Now, the norm of a sum is less than or equal to the sum of the norms, okay, the triangle inequality. So, this is less than or equal to j equal to n to m minus 1 modulus of lambda to the power of j. The norm of this, the shift does not change the norm. We remember that whether t minus 1 or go this side, when you integrate you can make the change of variable and get the same norm. So, it will be a fixed norm, norm g. All these are going to be equal to norm g. Whether it is L1 or L2, you write the integral and change the variable, will come back to the original norm. Okay. So, therefore, this comes out. Therefore, norm Sm minus Sn is less than or equal to norm g into summation j equal to n to m mod lambda to the power n to m minus 1. And we are done. Why? because mod lambda is less than 1, that is the tail part of the geometric series which converges, and therefore that will go to 0. So this tends to 0. So this can be made less than epsilon for nm greater than or equal to n epsilon, because mod lambda less than 1, and we are done. Okay. So that's a Cauchy sequence, and therefore it converges on that push star. Okay. There is a very famous statement by Bertrand Russell. See, if you look at carefully all great convergence theorems, finally you will somehow or the other compare it with the geometric series with mod lambda or mod x, mod c less than 1 and all, and that is the only series really honest to goodness neatly we knew the summation as 1 by 1 minus lambda and so on. So Bertrand Russell said, with all the talk about infinite series, the only series we have really summed up is the geometric series, nothing else. Okay. So in a sense, we simply fall back on the geometric series, somehow by hook or crook we convert everything finally to compare it with the geometric series. Okay. And this is typical in all iterative processes, and almost all the iterative processes the comparison will be finally with the geometry mod lambda to the power of n, where mod lambda is less than 1. That will be the typical proof of any iterative process. Okay. So now therefore what we have got is that outside the circle everything is in the resolvent, inside the circle everything is in the resolvent. So what is left is the disk. Okay. So now so let us summarize. So summary so far is this is a very nice example of how analysis works. Okay. Beautifully how many things come into the picture, the geometric series, comparison, Cauchiness of the and Banachness of x. Okay. Every part of analysis starts playing, Fourier transform, everything comes into the picture. We will see more, many more ideas of analysis coming into the picture. Okay. And that is only a lesson that you can't do spectral theory and good analysis of equations without a solid background of analysis, real analysis. Everything come into the picture. They are not isolated theorems, they are all built to finally answer questions. Okay. Right. So next, so summary. So far we have the point spectrum is empty, and all these points mod lambda not equal to 1, that is inside and outside the circle, they are all in the resolvent. This is all we have got so far. So now we come to the disk. See, that disk turns out to be an impenetrable disk, what is sometimes called natural boundary. Every point on that will be in the spectrum. It does not allow you some leverage of a friend in the resolvent sitting there, and through him you can get out from inside to out. It just completely blocks the resolvent into two disconnected parts. Okay. See, if you look at the series 1 minus x plus x squared minus x cubed, etc., the sum is 1 by 1 minus x. So it allows you to get out of the inner circle through other points. If you avoid the point 1, then you can get out through the other points and have friends there where the function is analytic and so on and so forth. So basically it is connected to the analyticity and all. So it's something like a natural boundary in the complex sense. But let's not get into those difficulties. So we have to next look at the set of all lambda which lie on the unit circle. Okay. We will show all these points are in the spectrum, but it turns out that in the two spaces that we got L1R and L2R, in the L1R case, if you look at the delay operator in the L1R case, all these points will be in the residual spectrum. But if you look at the finite energy L2R, the delay fellow, all these points will be in the continuous spectrum. So, the structure completely changes by looking at the same action, but on two different spaces. Okay. So, let us look at that. Okay. So, now the first step to decide whether something is now in the spectrum, well, certainly it cannot be in the point spectrum. We have ruled out point spectrum. So, the only chance of something here belonging to a spectrum is either the residual spectrum or the continuous spectrum. Now, the decision first comes whether the range of f minus lambda I is dense or not dense. If it is not dense, it will go to residual spectrum. If it is dense, it will be either in continuous spectrum or resolvent, depending on something else happening. So, first let us look at whether f minus lambda I f. So, let lambda belong, okay, we already have. So, let lambda like this. Look at f minus lambda I, look at whether is dense in X. Now, since lambda is on the unit circle, I can always write lambda as e to the I alpha, where alpha is between 0 and 2 pi, because everything on the unit circle is r e to the power of I theta is a complex representation, but r is 1, the modulus is 1. So, it has to be of the form e to the I theta. So, we can write lambda. So, let lambda be equal to e to the I alpha. It has to be of the form e to the I alpha, where alpha is between 0 and 2 pi. Okay. So, now whether range of f minus lambda I is dense in X. Okay, let me do some manipulations here. First of all, I should have brought it more explicitly. Anyway, case 1, X is L1R. You will see why I now bifurcate in these two cases. Okay. Suppose I am taking the L1 case. Now, look at this function. You will see why we will look, I mean, eventually you will understand why we look. H of t to be e to the I a t. Okay. It is a nice bounded function, cannot be more than 1. Whatever value of t we take between minus infinity to infinity, it is certainly modulus of h t is less than or equal to 1. So, note that mod h t is a very nice function, infinitely differentiable and at most 1 for every t in R. Now, I define a linear functional So, define a linear functional. I will explain to you why I do these things a little later. I am putting the cart before the horse. I am going to define a linear functional h on, what does that mean? H must assign a number with each element of L1R. Each element of L1R is a function. So, what it should do is it should extract a number out of every function in L1R. So, defined as h of h of any function x, it should be a number. So, I just integrate x of e to the I a okay, let me call it as h t x t dt. You just integrate with h t, that will give you a number, and that integral makes sense because this modulus is less than 1. So, it will be less than or equal to mod x t, and since x t is in L1, that will be a finite number. Okay. So, mod of h of x is less than or equal to minus infinity to infinity mod h t into mod x t into dt, but mod x t is less than or equal to 1. So, that is that, and that is less than or equal to norm of x, and therefore, what do you get? H is bounded, linear, functional on L1 R, and norm of H is less than or equal to 1. So, definitely it is in L1 star. So, it is in L1 star. Okay. So, I have a bounded linear functional on L1 star. Slowly we will build up, and then you will see why I defined this. Okay. Now, what I am going to do is, what does this bounded linear functional do on the range of f minus lambda I? What I will show, what we will see is that for every function in the range, h will assign the number 0. That is, h of g will be 0 for every g in the range, in that range, right. If for every g in that range h is 0, on the closure also it will be 0, because h is continuous, the bounded functional, it is continuous. So, h will be 0 on the closure, but if this were dense, the closure will be the whole space, and therefore, h will be 0 on the whole space, but obviously this integral is not 0 for all functions. There are functions for which this integral is not 0. So, therefore, let us go through that argument. G belongs to range of f minus lambda I implies there exists x in L1 R such that G can be written as f minus lambda I x. That is what is meant by this range. Okay. Something belongs to the range of f minus lambda I if it can be written as f minus lambda I of something. Okay. And therefore, h of g will be equal to integral minus infinity to infinity e to the I a t, because h of t is e to the I a t into, okay, let me first write that, h of t g of t dt, which is equal to minus infinity to infinity e to the I a t, g of t is f of x of t minus lambda x of t dt, which is minus infinity to infinity e to the I a t. What is f x of t? Shift x of t minus 1, that is the first integral, minus the second integral is lambda. What is lambda? E to the I alpha. So, I called it alpha. I will change this as I a, so that it becomes easy, otherwise I have to change everywhere. So, therefore, this will be e to the I a into integral minus infinity to infinity e to the I a t x t dt, right. Now, I will change the t to t minus 1. So, I will get t to t plus 1, that will become x of t dt, change of variable, and this I will take it inside as a constant. e to the minus I a into t plus 1 x of t dt, which is precisely 0. Therefore, h of g is equal to 0 for all g in the range, and h is continuous. Therefore, it implies h of g equal to 0 for every g in the range of f minus lambda. This implies h of g is equal to 0 for every g in the range f minus lambda I closure, because continuous functions the limit is also maintained. Okay. But h of x is not equal to 0 for every x in L1 R by very definition. Okay. Take the x to be 1 between 0 and 1, 0 everywhere else, then 0 to 1 integral e to the I a t is not 0. Okay. So, and therefore, range f minus lambda I cannot be equal to L1 R closure, because if it were, then hg would have, hx would have been 0. So, that says the range is not dense. If it is not dense, it must belong to the residual spectrum. Okay. And therefore, lambda, this belongs to residual. So, that implies lambda belongs to residual spectrum. So, summarize, we got everything now. The residual spectrum is all the remaining. So, the circle is in the residual spectrum and everything else is in the resolvent spectrum. The point spectrum and the continuous spectrum are empty, there is nothing in these two. The residual spectrum is more difficult to handle, okay, because then it says that other part we do not even know what to do. The range of f minus lambda I closure, up to that we are able to define the inverse, you have 1 1 and on 2, but above that completely dark about what we should do about the inverse. In fact, we can define the inverse in an infinite number of ways, and that leads to pseudo inverses and so on and so forth. What we learn in matrix theory, analogous things we can do, okay, what is known as the pseudo inverse, and we can even extend notions like the singular value decomposition and so on and so forth. What I will do is I will do those things more easy setup, namely the Hilbert space setup. Okay. Okay. So, now this was the case when we did it in the L1R. Okay. So, next case is what happens in the L2R case. The same, this circle now completely changes its structure. It is now it is going to be in the continuous spectrum. See, in the I defined h of t to be e to the I a t. Now, if I use that, and if this x is in L2R, this will not define a functional on L2R, because for a function in L2R that integral may not be finite. Previously this became finite because this integral was finite, but now when you are in L2R you will have only the square of the integral is finite. There are functions for which the square of the integral over R is finite, but the integral itself is not finite. L1R and L2R, there are things in L2R which are not in L1R. So, I can't use this specific example to show that that is not dense, but then I will use something else to show it is dense. Okay. So, now we will almost, so what we did in the previous case was the following. I had a bounded linear functional which vanished on the range, but did not vanish on the whole space, that was the e to the IAT integral. There was a bounded linear functional which vanished in the range, but did not vanish, but still did not vanish on the whole space. But now we will show whenever something vanishes on the range, it must also vanish on the whole space, and therefore that range must be dense. Okay. So what basically you are saying is, when you have a continuous linear functional, it will vanish in the whole, if a set is dense, if and only if whenever a bounded linear functional annihilates that, it must annihilate the whole space. That is what the characterization of the zero functional, or the characterization of the dense set. A set is dense if and only if when something continuous vanishes there, it must also vanish everywhere. That is the main point of a density argument. Okay. So, in this case, remember in the little, when we studied linear functionals, we said any linear functional on little L2R is generated by another element in the L2R, so that it can be written as the dot product, right, Figi. Same argument works here. When you are in L2R, any linear functional is generated by another L2R functional, another L2R function, and it is written as a dot product. The dot product there was a sum, now it will be an integral. Okay. So, let H belong to L2R star. This implies there exists a little h in L2R such that h of x is equal to integral minus infinity to infinity ht xt dt. Because you want a bar, but we can take the definition in that bar there. The conjugate can be observed in the function h. Okay. Okay. So, now what does that tell us? Suppose h belongs to L2R star and h of g is equal to 0 for every g in range f minus lambda I. I will just write the steps, then claim h of g, h of x equal to 0 for every x in L2R. That is, h must be the 0 functional. Okay. Hence, range f minus lambda I is dense. So, the only question therefore is, it will not be in the residual spectrum, because now the range is dense. It will not be in the residual spectrum. The only chance is either it is in the continuous spectrum or it is in the resolvent. So, let us see whether it can be in the resolvent. Okay. So, therefore, lambda belongs to continuous spectrum or lambda belongs to the resolvent. Now, here also a very nice thing comes into the picture. Again, Fourier transforms will come into the picture or whatever it is, but it is much easier, very nice. I mean, a lot of analytical ideas will come into the picture. Now, suppose lambda belongs to the resolvent. What does it mean to say that lambda belongs to the resolvent? Which means I can come back, the inverse map is also bounded. That means for every g I can solve the equation f minus lambda I x is equal to g. Okay. So, therefore, for every g in L2R, there exists x in L2R such that f minus lambda I x equal to g. But what should be x? You see, what does that say? F of x, that is xt minus 1 minus lambda xt must be equal to gt. Now I can't go around doing the iteration now, because I have got mod lambda equal to 1. Previously I had mod lambda less than 1, so I could get the iteration and make it converge, but I can't make it converge now. So I am going to directly handle it. I go back to Fourier transform. Whenever there is trouble with in time domain, you go to the Fourier. If I take the Fourier transform, now the L2 Fourier transform, this is e to the I omega x hat minus e to the I a x hat omega is equal to g hat omega, or x hat omega must be equal to g hat omega divided by e to the I omega minus e to the I a. Okay. Now the x should be in L2R. If x is in L2R, its Fourier transform also has energy, the spectral energy is maintained, okay, power spectral energy, whatever you want. The energy on the times the other side is also the same, if you put the 1 over root 2 pi correctly. So the Fourier transform and the original function have the same norm. So therefore this fellow must also be in L2R. If this fellow is in L2R, this fellow must be L2R. The right hand side must be finite square integral. Already g hat is square integral, because it is the Fourier transform of an L2R function. Now we can write this as g hat omega into h hat omega, where h hat omega is 1 by e to the I omega minus e to the I a. So the right hand side is the product of two functions. One of them is already in L2R, and the product must also be in L2R. Okay. And this must happen for every g hat, because this happens for every g I must be able to x. But there is a simple theorem in analysis which says, if the product of a function with every L2R function is also L2R, then that function must be bounded, but that fellow the h is not bounded. So that is what is, this is not in L infinity. So this implies h hat must be in L infinity contradiction, that is bounded, it is not bounded, and therefore lambda does not belong to this. So this is out, so the lambda belongs to C sigma. So in the two cases what we have got is that circle definitely is the spectrum, but in the case of L1R it is a residual spectrum, in the case of L2R it is a continuous spectrum. Inside and outside the circle it is the resolvent. Okay. So what this says is, basically if you now solve the equation f minus lambda I x equal to g or y, suppose you are now having a functional equation which is x t minus 1 minus lambda x t is equal to y t. Given the y t, you want to find the x t. When you solve the functional equation, it says for every lambda inside and outside, the solution is available, and therefore the solution will be a function of lambda, and it will be an analytic function of lambda. But the fellow inside, he cannot be continued to outside in the, because that circle remains a natural boundary for this analytic function. Okay, this is a complex analysis thing that is involved there. So it's a very fantastic example, because it has many things in it. It has analysis in it, it has Fourier transform in it, it is iteration in it, it's a convergence of the iteration in it, it has linear functionals in it, the idea of dense sets in it, and the characterization of dense sets in it, the complex analysis ideas of natural boundary. It is a phenomenal example and a very simple operator. And it also it has the fact that if you are looking at it in two different spaces the same action, the structure of the spectrum itself is different. In one case something is residual, in another case the same thing is continuous. So it's a very fabulous example. It's analysis in all its glory. Okay, this example, and there are many such examples. for spectrum, calculating the spectrum, I had when over the years teaching, I had collected I had given exercises, number of exercises, every year different one, can find the spectrum of the following operator, as more or less like at the end of this, instead of a test, a term paper, find the spectrum of the following operator. Okay. So, and this was something that popped up this morning. So, I thought probably I should say that to you, because it brings analysis in its glory. Many things are in this. Okay. So, that's where the cleverness of analyzing the equation is. Here first, the fact that lambda belongs to resolvent means we are trying to find out for what lambda this equation is solvable. So, that is the existence questions we are answering, and then we showed that for mod lambda less than 1 we could find the solution by an iterative process. Okay. And for mod lambda greater than 1 we can convert it to an iterative process, because that is how we showed that the inverse exists. Okay. So, in both the cases we converted it to a iterative process. So, therefore, it has not only has existence of solutions, how to find the solutions, when does it converge, what is the rate of convergence, everything is there, because it is compared to the geometric series. So, it is sort of a complete thing about package about how you handle the equations system, functional equation involving the shift operator. Okay. Now, it is a little, you see here when we are in L1 and L2, Fourier transform came to us help, which we all know. Okay. Let us push it to LP. Now, what is this Fourier transform then? Okay. So, it is a little bit more, it takes you further up in the analysis. Suppose the same shift operator, now I look at in the LP space where P is not 1 and P is not 2, but something else. Now, some of this analysis may get bogged down, but some of the analysis will go through. Okay. For example, here the analysis was that whenever you had a linear functional, there is a corresponding H which generates it in L2. In LP also, for every linear functional there is an LQ function which generates it. Okay. Only thing in L1 was a little difficult. We somehow concocted an L infinity function which answered our question. So, this is typical because L1 is not reflexive. L1 star is not L1, whereas LP star is LP for all other P. So, in all those cases this sort of representation of functionals gets you the answer, but L1 you got to be a little bit more careful. Okay. So, that is the situation. So, now this is why spectrum is important. It tells you all about solving equations. Okay. Equation of the form f minus lambda I x equal to y. I said almost all our partial differential equations etc. time dependent. By removing the time dependence, the Laplace transform can be converted to this form, all linear equation, the classical equations. That is where the spectral theory developed. Okay. In the matrix case it was easy. As you go up and up in more complex spaces, a lot more analysis is asked for. Okay. So, what I will do is I will next move to Hilbert spaces, and then I will bring in the analogy with these fellows with the matrix theory and see how does it proceed. Okay. What are the class of operators for which we have complete analogues of the matrix theory. We can talk about pseudo inverses and so on and so forth. Okay, I think I will stop here.